In this video, we're going to discuss exponential functions. All right, before we get all the way into exponential functions, we're going to look at this example. We have two scenarios. In scenario A, we have a town that has a population of 1,000 in year zero or during the initial year, and it grows by 50 people per year. And then we have scenario B, which is a town that has a population of 1,000 people in year zero, and it grows by 5% a year, right? So one town grows by 50 per year, the other town grows by 5% per year, right? And so we're going to calculate the number of people that are in that population or in that town through years t equals 0, 1, 2, 3, and 4. And we're going to fill it in this chart. What we're also going to do is at the same time, we're going to find a formula for the population. We're going to use P for the population and T as our variable for the year, right? Now we already know that both scenarios start with the same population at year zero. In population A, after a year, the population should be 1,050 because all I have to do is add 50 people to get to the next year. I add 50 people there. If I add 50 more people to 1,050, I get to 1,100. I get to 1,150. And then in year 4, I should expect the population to be 1,200. So what I'm doing here is I'm adding 50 each time, right? And so with that, I can come up with the formula for that. For a 1 unit increase in year, which is our t, which is our input variable, our output variable increases by 50. That is a perfect setup for what we call slope. This is a linear function. And so if I want the population for scenario A, it's going to be P equals, all right, mx plus b, right? We can do mt plus b because t is our input variable. Well, our slope is 50 because that's the change in y, or our output for 1 unit change in our input. Our input variable is t, plus our vertical intercept. Remember, the vertical intercept is the value of your output when your input equals 0. Well, my input equals 0 at year 0, my output is 1,000. So it's going to be 50t plus 1,000. Simple enough. That's linear function. Let's look at the other scenario where the population of the town grows by 5%. So remember, to take a percentage of something, you multiply that number by the percentage and add the original amount, right? I'm going to write this way, right? If I want to add 5% of 1,000 to 1,000 to calculate a new population, I'm going to do 1,000 plus 5%. I change that to a decimal, which is 0.05 times 1,000. Now you can put that in your calculator and you're going to see that that's equal to 2,050, right? I mean 1,050. But what I'm going to do, since I want to come up with the formula for this, is I'm going to do something very interesting here. Notice both of these terms have a 1,000 in them, right? There's understood to be like a 1 right here in front of that 1,000 multiplied, and that's a 1.05 multiplied by 1,000. Well, if I were to factor out 1,000, just stay with me here. Then if I factor out a 1,000 from both of these terms, I'm going to be left with a 1 in that first term and a 0.05 in that second term, which is the same thing as saying 1,000 times 1.05. All right. And you put that in your calculator, you're going to get that same 1,050. This right here is going to help me come up with the formula. That is why I'm doing that there. All right. That is exactly why I'm doing that there. All right. So I'm going to remember that 1,050 is what I calculated here, and it's the exact same thing as 1,000 times 1.05, right? Remember, when two things are equal, you can replace one with the other. Keep that in mind as I go forward here. Now, if I want the population in year 2, then I take the population after year 1, and I'm going to add 5% of that population in year 1 to that. Okay? Now you can put that in your calculator. I did this on my own. I think you get 1,102.5. All right. Now what I'm going to do here is something similar that I did above, right? Notice there's a 1 understood to be there. And so if I factor out a 1,050, I'm going to have a 1 plus 0.05, which is 1.05, right? which is very similar to what I had over here, but now I have a 1050. Well, as I said before, 1050 is the exact same thing as this right here. So anywhere I see a 1050, I can replace it with 1000 times 1.05. And so I'm going to do that here. Instead of writing 1050, I'm going to write 1000 times 1.05, right? And I still have this original 1.05 here. And what we know is that when we multiply something by itself, we can write it as something squared, the something squared, right? So I could write that as 1000 times 1.05 to the second power. So when I at year one, I had 1000 times 1.05 to the first power. In year two, I had it to the second power. As you can probably guess, you're going to get 1000 times 1.05 to the third power. And when year four, you're going to get 1000 times 1.05 to the fourth power, right? Just so you know those values, it's 1157.625 after 3 years. And then it's 1215.50625 after 4 years. I know that we're talking about a population. However, and we usually don't have half of people or 0.65 people or 0.5065 people. I'm just giving the real value here, right? But what this stuff does, this factoring and all that stuff does, is it helps us see that each year, from one year to the next, all we're doing is we're multiplying by 1.05, right? So what I did here was I multiplied by 1.05. Here to here, here to here, multiply by 1.05, multiply by 1.05. That's why the power is increasing. Multiply by 1.05, right? That's a sign that we are in the case of this type of function here. And if I wanted to write my function, notice it's going to be, for town B, P equals 1000 times 1.05 to the t power, okay? And that is my function here. Functions of the form written in part B are for town B here. Functions that are written in that form are called exponential functions. So not only do we have linear functions that we study, we also have exponential functions. And so with exponential functions, we want to remember something, right? Linear functions have a constant rate of change. It's a constant rate of change. It is a numerical value, a constant value that gives you your rate of change, right? And here it was 50, all right? The difference between a linear function, which is given in this chart, and an exponential function, which is given in this chart, is that it has a constant percent rate of change, all right? Exponential functions will have a constant percent rate of change. This means that there will be a constant ratio between consecutive values in the independent variable. And so if I go back to this chart here, I'm going to look at these values here. I know that I multiplied by 1.05, right? So one way to tell whether a chart is linear versus exponential. Linear, you add or subtract the same number to get to your next y value, as long as your input values are consecutive or split evenly, separated evenly. For exponential functions, you can multiply or divide by the same number, and that will give you your exponential function. And so since division is multiplication by the reciprocal, you can think of it that way. All right. One way to tell whether a function is exponential when you have a table of values. So let's say I didn't know this piece right here that said it grows by 5% per year. What I could do, all right, year zero, year one, right? I know the value at year zero. I know the value at year one. If I take year one and divide it by year zero, that should equal what I get when I take year two and divide that by year one. And that should equal what I get when I take year three and divide that by year 2, and so on and so forth. And what you're going to see is that all of those equal that 1.025. All right, sorry, 1.05. Okay. And so that's a way that you, if I were to give you a table of values, you could tell whether a function was exponential or not. And that encompasses that consecutive ratio statement that I did, right? There will be a constant ratio between consecutive values of the independent variable. All right. So let's talk about the parts of the exponential functions. Exponential functions generally come in the form P of t, right? So it's a P as our output variable. Our input variable is t. Everything else is going to be replaced by a number, right? For instance, it equals P naught or P sub 0 times a to the t. P sub 0 or P naught is your initial quantity, right? It's also your vertical intercept, all right? It's the value of your output when your input equals 0. A has two names. It can either be a growth factor, that's when A is greater than 1, kind of like in the example that we just did, or it could be a decay factor. That's when A is a number between 0 and 1. It's a fractional number, something like 0.95, right? That would be a number between 0 and 1. It's the decay factor. When there's growth, when A is a growth factor, we are experiencing exponential growth. That means if you increase T, your output is going to increase. That's exponential growth. You have exponential decay when A is between 0 and 1 or a proper fraction. That means if I increase my T, my output is going to decrease and decay. Now, the example that we did, the thing that was in the place of A is that 1.05. Notice as I went from year to year, my population grew. All right, it grew, it got larger. All right, notice 1.05 in this formula here is greater than 1. It's always going to grow as long as this is greater than 1. All right. Now, some people like to write exponential functions in the following form. P of t equals P naught times 1 plus r to the t, right? And so instead of using that a there, some people like to see the actual percentage by which you're growing or you're decaying, all right? And so notice that in our example, so a is the same thing as 1 plus r, all right? R is the decimal representation of that percent rate of change. When I looked at the example that I just did, we said that this was growing by 5% per year. All right, that town population was growing by 5% per year. And so since A equals 1 plus R, and R is that representation of that percent that you're growing by, if I do 1 plus 0.05, I get that 1.05. Had they said decayed by 5% per year, then instead of having a plus sign, I would have had a minus sign, and that would have been a 0.95 as my A or my 1 plus R. And so this R right here is going to be a percentage. It's going to be positive when you have exponential growth, and it's going to be, so the positive is here. I'm going to pause. And it is negative, I'm going to put neg. And if R is negative, that means we have exponential decay. We hadn't seen an example of that yet, but we will see an example of that. All right. So you have two ways that you can represent your exponential growth and decay in your exponential functions. They're exactly the same, but some people like to see the R, and some people don't like to see the R. I preference this here, and I just understand that, oh, if it's above 1, I have growth. If it's less than 1, I have decay, right? Or if I think about the R, if R is positive, I have growth. If R is negative, I have decay. All right. Let's look at this example here where we apply this stuff in a real life example. The company that produces Cliff Notes, which are abridged versions of classic literature, was started in 1958 with $4,000 and sold in 1998 for $14 million. Find the annual percent increase in the value of this company over the 40 years. All right. The clue in this example that lets me know that I am in the exponential case is that I see an annual percent increase. All right, annual percent increase. So when I see that, I should automatically think, okay, I'm in the exponential function case. I'm not in the linear case, I'm in the exponential function case. So the formula that I'm going to remember is P of, I left off the P of T, but I put P equals P naught A to the T. All right, I just gave the function's name. All right. So whenever we come up with the function, well, our goal is to find the annual percent increase. Okay. We know in 1958, it was worth $4,000, and in 1998, it was worth $14 million. Right? So it's telling me the initial amount that it was worth was $4,000, right? That's the initial. My goal is to find the annual percent increase, right? The annual percent increase is a rate. So basically, I want to find R. Here, I have P naught A to the T, right? And I have to remember that A equals 1 plus R. And so if I find my A, all I have to do is see how much is over R over 1, and that's my R, all right? For me to do that, I've got to get rid of these some of these variables here in this equation here. So one of the things I know is that initial quantity, which is $4,000, which is the value in 1958. Remember, that's a vertical intercept, right? That means if I plug in 0 into this function, my output would be 4,000, right? That's what I have here. I don't know my A. This is what I want to find. What I'm going to use to help me figure this out is I'm going to use this other information here, which is the fact that in 1998, I have 14 million, the company was worth $14 million. 1998 is 40 years from 1958. So if I were to put 40 into my function, since I know it's an exponential function, into this function, my output would be $14 million. Now I have an equation with one single variable that I want to solve. And all we have to do is remember how to solve an equation that looks like this. First thing you do is you divide both sides by 4,000. We're going to get 3,500 equals a to the 40th power. Then I take the 40th root of both sides, right? Remember, when you have a squared, like if that was a squared equals 3,500, you would take the square root of both sides because the square root, there's the index 2 understood to be there, and the square root and the square cancel each other out, right? And same thing happens when you have the 40th root. All right, another way to look at that is, okay, I'm going to go back to square roots because a lot of people know square roots very well. Another way to solve that is to raise it to the 1 over that power, which is the 1/2 power. I know I just changed that number from 3,500, sorry. But if I have a squared equals some number, taking the square root is the same exact thing as raising something to the 1 over 2 power, right? Because the index for a square root is 2. Right? Remember, when you raise a power to a power, you multiply your exponents. And when you multiply 2 by 1/2, that's a to the first power, so we don't have to put it there. And then you can put that in your calculator to see what that value is, all right? And so that's what we have here. We took the 40th root, or if you wanted to, you could have done this here. You had 3,500 equals a to the 40th power. It's equivalent. These are exactly the same things. It's just written differently, okay? Those become a 1, and so we have 3,500 to the 1 over 40th power. This and this are exactly the same, all right? So those cancel. I'm left with a on my right-hand side, and I'm going to put that in my calculator, and I get approximately 1 point, let me see what I had, 2263, okay? So if I wanted to, now it didn't ask me to write the actual function, but my exponential function here would be 4,000 times 1.2263 to the t power, right? And so my a was approximately 2263. The goal was to find the annual percent increase, right? So I want to know what percentage was my increase. Well, I know that this is exponential growth because this number is bigger than 1, right? And so since A was 1 plus R, my annual percentage is the amount that's above 1, right? And so if I have 1.2263, the amount above 1 is 0.2263. And if I wanted to write that as a percent, I would multiply by that by 100, and that would be 22.63%. That is the solution to this problem. And for now, we're going to stop here. We're going to get a lot more information about exponential functions. Actually, I'm going to do one more thing. Let's talk about the graphs of exponential functions and then a special exponential function. All right, we want to talk about the natural exponential function. That's f of x equals e to the x. That is called the natural exponential function. All right, e is an irrational number. All right, it's almost like pi. Pi is approximately 3.14, approximately 22/7, but it's a non-repeating, never terminating decimal. And so that's why we have a pi button on our calculator, or we use that symbol to represent it, because we can't write out all the digits, right? E is another one, right? And it's a specific number that comes up in natural applications. And so the natural exponential function is actually f of x equals e to the x. E is Euler's number, and it's approximately 2.71828, right? So when I see e, f of x equals e to the x, I'm also seeing f of x equals 2.71828 85828, so on and so forth, to the x power, right? So that's one that we'll look at eventually because there are some natural applications that applies to. I want to look at the graphs of exponential functions. They are nonlinear functions, all right? All of the graphs here on the left have a base, the thing that I'm raising to the t power, that's bigger than 1.5, 2, e, which is 2.718, 3, 5, 10. As you can see, the larger the base, the numbers 2, e, 3, 5, 10, the quicker it increases, right? But these graphs represent exponential growth because a is greater than 1. They're increasing and concave up graphs, all right? And since there's no P naught there, the P naught in each of these examples, there's understood to be a 1 multiplied in front of each of these. They all go through the point 0, 1, okay? Now, in the graphs to the right here, we have exponential decay. And the reason why I know that is because that base A, that is a number less than 1, right? So we have exponential decay. So these are values that are less than 1. We're not going to ever have negative values. That's why I stop at 0 here. But they are exponential decay. They are decreasing, but they are also concave up functions. All right. Not only that, notice there's a 1 in the space of the p naughts in these graphs here, right? And when that is the case, they all also go through the point 0, 1. All right. I'm going to stop the video here. We'll get to some more exponential function stuff next time.